This is experiment 8, the bromination of cholesterol. So this is an electrophilic addition reaction to the double bond at carbon atoms, the carbon-carbon double bond at C5 and C6. And so we're going to start with around 100 milligrams of cholesterol, and we are going to brominate it with a solution of bromine and acetic acid, which has been buffered with sodium acetate, and tertiary butyl methyl ether, a.k.a. MTBE, as it's abbreviated, is the solvent to firstly dissolve cholesterol, and this is all going to occur at room temperature. And we're going to be able to watch the solution of bromine, which is red-brown, change color as we add the solution to the reaction mixture of cholesterol. And so today we are starting out with, we weighed out 101 milligrams of cholesterol. So you can see that cholesterol is just a nice white looking solid, nothing spectacular. And it came from this bottle, which says that it's ultra pure grade. And so the first thing that we're going to do is we are going to add the cholesterol that we weighed out at the balance. This is 101 milligrams. We're going to add this to our 10 milliliter Erlenmeyer flask. And you'll see that if you look a little closely at the weighing paper, the cholesterol is stuck. And some of it is sticking to the weighing paper, so I'm just going to push it down in there with my glass stir rod, which I'm going to use shortly, to try and be sure that we've got most of it into the flask. All right, and then I'm going to walk over to the fume hood, and we are going to add 2 milliliters of MTBE, as our salt. So this is methyl tertiary butyl ether. IUPAC, you're supposed to name it alphabetically, so tertiary butyl methyl ether, or you could also call it 2-methoxy-2-methylpropane. However, methyl tertiary butyl ether is named in this order due to history. It used to be a former gasoline additive. And so my pipette can't reach down in there, so I'm going to pour about 2 milliliters into this graduated salt. And why don't we go ahead and we can rinse the weighing paper as well to really get all of the cholesterol in there. And then we can discard that weighing paper. And so let's see, here's my 10 milliliter Erlenmeyer flask. Close this bottle. And if we swirl this around, will it dissolve at room temperature? Yes, it does. So cholesterol, at least in this proportion, 101 milligrams dissolved readily in 2 milliliters of MTBE at room temperature. I can tell you that this room temperature is about 20 degrees. It's very cold in here today. All right, so then the next step is that we are going to add 110 microliters of solution of bromine, which I had just freshly prepared. So, the bromine solution is 0.7% weight sodium acetate and 7.9 weight% bromine, all dissolved in glacial acetic acid. And so we need approximately 110 microliters. So we've got our 20 to 200 microliter automatic pipetter, and right now it's set to 127 microliters, so we need 110 microliters. Okay, and this is going to vary depending upon obviously the amount of cholesterol you've gotten in there, and then also the freshness of the solution. Right? Because as the solutions age, the bromine leaves and actually evaporates away. So this is 110 microliters. You see, it's not very much. And what we're going to do is we're going to add it drop-wise, because what's going to be fascinating is that it's going to take on a yellow color with each drop. But then as we swirl it, the color goes away. It's almost like a titration. So with every drop, and then the color disappears, that means that amount of bromine has already reacted with the carbon-carbon double bond. So the cholesterol's gotten up there on the sides of the flask. So if we add the whole 110 microliters, now we see the color is persistent. If we stir it, swirl it, I should say, we see that the yellow color is persistent. So this is what we're looking for. We want the color to persist because we want the cholesterol to be our limiting reagent. Okay? So we've just swirled this around at room temperature, and we see that the yellow color has persisted. In our experience, though, we are going to wait a little bit longer and see if that color persists, because to my eye right now it looks like it's lightened up a little bit even. So we're just going to wait for a second, and then we might add more. So just hang on to your seats. So as suspected, the yellow color is no longer persistent, so we're going to add some more bromine solution. I'm drawing up another 110 microliters, but I don't think that we're going to need it all. So just a couple more drops and see. And we should see some cholesterol dibromide start to precipitate out. But that classic yellow color happens to be disappearing quite readily. So we just want to make it a little bit more yellow, but not orange, not too much. So we still don't see any precipitate, and that yellow color is still going away. So now we've added a total of 220 microliters. And eventually we're going to chill it on ice. But still, yet again, that yellow color is going away. So let's keep going. This is why it's cool that it's convenient in this sense that we've got a colored reagent, because we can tell right away when it's all used up. And remember, again, we want this to be the reagent in excess, and so that cholesterol is our limiting reagent. So the number of millimoles of cholesterol is our theoretical yield of cholesterol dibromide. steroid that we were using before. Let's see. So there is some white solid that's catching up towards the top, but is that actually our product? Because it's still, that yellow color has not persisted. It's more of a milky. Yeah. So we can see some solid form down there, right? And especially on the tip of my glass stir rod. But I don't think that we're done yet adding bromine. So let's add now a total of 440 potentially. Let's add a couple more drops and see. Well, more solid is forming, so that's good. That's our cholesterol dibromide. So now I'm going to add the rest. So now this is total now 440 microliters of our bromine solution. Let's pick it up and take a look with our glass stir rod again. So we see that the solid that's stuck to the glass is a white solid, and that's true for our product. But the bromine color is still just not persisting. But this is good otherwise in terms of the amount of product precipitating anyhow. So we know that the reaction is working. It's also worthwhile to note that there's no exotherm, at least to my touch. Still seems like it's the same temperature. So let's do 550. It's possible I made the solution incorrectly. Who knows? 550. I mean, you certainly cannot over-brominate cholesterol. There's only one double bond. The solid that's precipitating. There's hardly any solid. Filtering this is going to be interesting because it's just mostly solid. And again, there's this. This is fascinating. I think we must have made the solution incorrectly because this doesn't usually happen. So I'm going to add 2 more milliliters or so of methyl tertiary butyl ether. There's 2 more. Just so we have some headway. See, some solid moving around rather than just a slush. It's no longer a sort of like a slush going on in here, but again, that we don't see the yellow, so we cannot presume an excess of bromine. So whatever concentration solution that I might have accidentally not made properly hasn't been good. So this is 660 now. Let's see if this will maintain the yellow color. Looks like it might. Okay, so yeah, this is good now. This starts to disappear again. We'll add more, but make note, the bromine solution that we added 660 microliters total. How we prepared the solution, in order so that we can go back and see if we did it properly, we added 700 milligrams of sodium acetate and 2.53 milliliters of bromine to make a 100 milliliter solution in glacial acetic acid. So, according to our calculations, that should make sense because this is weight percent. So it's just possible that we finally figured out a potential textbook error in the procedure, which would explain some past fall failures. But anyway, it's good for you guys to be able to see an actual experiment where we're testing things out. So that's sort of lucky, I think, anyway. All right, so that yellow color is persisting. All right, we'll let it go for a little bit longer and then see if it continues to remain this pale yellow color. So our color has persisted now for about 7 minutes, so we're good, and we can see that it's maintained this yellow color, but keep in mind that the solid itself is white. So now I'm placing my 10 milliliter Erlenmeyer flask in a ice water bath, which is now, since it took so long, just mostly water. Hold on. So I've nestled this 50 milliliter, I've nestled the 10 milliliter Erlenmeyer flask in a 50 milliliter beaker with ice water. This is in hopes that more cholesterol dibromide will precipitate out a solution. But upon easy inspection, we see that that doesn't seem to be an issue at all. But regardless, we're going to chill it. Okay, so now at this point, we are going to make our wash solution, which will be used in order to rinse the 10 milliliter Erlenmeyer flask in order to try and achieve a quantitative transfer of our product when we go ahead and vacuum filter it. So the procedure says to add 1.4 milliliters of glacial acetic acid into a 10 milliliter graduated cylinder, and then from there add MTBE so that it hits the 2 milliliter mark. So I'm just going to use these 9-inch pipettes to draw up these two liquids. And almost 1.2, so I gotta get a little bit more. That's 1.2. And now the meniscus is at 1.4. So we're good. So that was our glacial acetic acid. Now we're going to use a new pasture pipette. To draw up enough MTBE to make our solution. Which is only going to be 0.6 milliliters, of course. You can almost see it sort of floating on top before it starts mixing. We get a little bit more. But now the meniscus is right at 2. All right. And so I'm just going to draw this up and down the pasture pipette to mix our solution to make sure it's homogeneous. All right. And so now this solution we want to keep cold. We want to chill it. And in order to do that, we are going to use an ice water bath contained in a 400 milliliter beaker. It's important to note that we had to have some MTBE in our solution because if we had used just pure glacial acetic acid, the melting point is positive 16.16, and so what would have happened is that if we put it in an ice water bath, it would have just frozen. So the MTBE depresses its freezing point so that we can use a cold solution of acetic acid instead to wash our product. So I'm going to get a, well actually we're going to migrate over to the lab bench now, and we're going to vacuum filter our cholesterol dibromide, and then we're going to use our cold wash solution that we just prepared to try and affect the quantitative. Okay, so here's our cholesterol dibromide reaction mixture in the 10 milliliter Erlenmeyer flask in an ice water bath contained in a 50 milliliter beaker. Here we've got our wash solution contained in a 400 milliliter beaker in ice water. And here's, of course, our vacuum filtration setup. We've got our Hirsch funnel, rubber collar, 25 milliliter sidearm Erlenmeyer flask, and we're going to turn the vacuum on. And so this cholesterol dibromide is notorious for sticking to the sides of the glass. So I'm going to really try and motivate it to really come out by using my glass stir rod, rather than just trying to push it, swirl it and let everything come out via gravity. I'm going to give it a push. And you see, once it hits that filter paper, the yellow color is gone because the vacuum is sucking up the bromine solution and therefore the yellow color. So that wasn't too terrible. The only downside of doing this outside of the hood is that it smells like vinegar and a swimming pool, because you've got bromine and acetic acid slightly in the air. We've got very good ventilation going on. All right, so this is pretty decent, I think, for first round of just trying to get it out. So now comes the wash round. Where we're going to use our solution. And so I'm going to take a very small aliquots at a time, because I want to rinse this as many times as I possibly can, because you can see how much is stuck here. So first thing I'm going to do is I'm going to rinse my stir rod because I can see that a lot of it has stuck up on the side. I can leave that there. And this is going to be rinse number 1. You can see it's already not enough, but so now I'm trying to direct where the liquid is going by using my glass stir rod. Swirl and then agitate again. Much out every time. Right. So you can see it's clearly rinsing the walls of the flask. Again, trying to get most of it mixed in. And you see that the yellow color has gone away as well, because with each wash it's also taken away some of the excess bromine. So it seems like the most now is really just at the neck, the top of the Erlenmeyer. So I'm going to try and rotate it as I turn it into the flask. And now let's see if we even have some left, because I can't even see how much wash solution is left. Oh yeah, we've got plenty, so we're doing a great job. So the nice thing about the glass stir rod is you can really direct where the liquid is going, and then you don't have to contaminate your pasture pipette. So this time I'm not using my pasture pipette to rinse the sides of the glass. In the end I can. So we're being extraordinarily thorough. There's a lot of stuff there. Trying to maximize our yield, isolating as much as we can. And now let's just do this as the remainder. Rinsing the glass stir rod now, getting most of that dibromide off. Now I can use my pasture pipette. Seems like the stuff that's up there is actually on the outside of the neck. So I'm going to use that, slowly drop it down in there on the outside of the Erlenmeyer flask. And now it's getting the solid that stuck to the outside of the neck. So how good did we do? Well, that's pretty clean. There's just a little bit left, so that's okay. And we're totally out of solution, yes. So now we're just gonna let air pass over this for a little bit. Acetic acid is extremely volatile. even though it has a very high boiling point of around 118 degrees. And that has to do with the intermolecular hydrogen bonding. It forms a dimer, actually. So even though you'd expect a lot of hydrogen bonding going on, acetic acid is not very viscous at all, and it evaporates away pretty readily. So we're just going to let this go, and then we're going to collect it, contain it in the pterid weighing boat that we have, and then calculate our mass and then our percent yield. Okay, so we've allowed air to pass over our cholesterol dibromide solid for about 10 minutes now, and I went ahead and used my micro spatula to sort of break it apart, and it looks pretty bone dry, which is not surprising. So I'm going to turn off the vacuum, and I'm going to take my Hirsch funnel off. Remember, I keep a little piece of weighing paper under the aluminum weighing dish just in case some falls out. And it was nice that I broke it apart beforehand, because this stuff, it was really a big chunk. Try and get the majority of it in there at first. As you can see, unlike benzocaine, it's not as free-flowing a solid. Right? It's still pretty attracted to the porcelain. And we definitely had to make sure it was dry, otherwise it just turns into sort of like this paste. Now I'm really scraping the sides of it. Trying to avoid the filter paper for now because I don't want to scratch it off. Now I'm going to go after the filter paper, and not too rough because I want to scrape up the solid. I don't actually want to scrape paper and think that that's my product. That would lead to a false yield. Even sticking to the edge here. Now, there's our filter paper, and anything else I'm just going to really go at. Can you hear me digging into it? That's how stuck it is. But again, at some point, this isn't that precious of a material, so you can leave some behind, but you do want to show that you got the best yield you possibly could achieve. So I'm trying to get most of it in there. But at some point, you ask yourself, what's more important? This or going outside? All right. So another thing to pay attention to is look at the filtrate here in the sidearm filter flask. This potentially could be more product. So this is a source of error in terms of whether or not we have a low percent yield. And just like I had mentioned before about the weighing paper under here, some of it did spill on the other side of the aluminum boat, so I'm going to go ahead and try and get these little pieces of my dibromide in there. But again, it's just sticking to everything. Okay, so now we're ready to go over to the balance, get the mass, and then calculate our yield. So we're at the balance. We've got our cholesterol dibromide in our weighing boat. I tared the balance. See how much we've got. All right, so our tare weight was 0.416 grams for the aluminum weighing boat. And right now our balance reads 0.504 grams. So 504 minus 416 is 88 milligrams. And so 88 milligrams was our actual yield. And so now let's talk about the theoretical yield. So our limiting reagent was cholesterol, and our reagent in excess was bromine, and we were sure of that. And so in order to calculate the theoretical yield, you use the limiting reagent to tell you the maximum amount of material that could possibly be synthesized in this reaction. So, since cholesterol was our limiting reagent, and we started with 101 milligrams, we need to know how many millimoles that could possibly be made of the product. So we're going to take 101 milligrams, multiply it by its molar mass, so we're going to get number of millimoles over 386.66 milligrams. So we're dividing 101 by 386.66. Milligrams cancels out, and we get the number of millimoles, and it's 0.26 millimoles. This is the theoretical yield in millimoles. But since we just measured this cholesterol dibromide in its mass units, we need then to take 0.26 millimoles, the theoretical yield, multiplied by the molecular weight of cholesterol dibromide, 0.26 times 546.47 milligrams per millimole. Millimoles cancels out, and we get the number of milligrams of cholesterol dibromide that we could theoretically make. The maximum amount is 142 milligrams. All right, so this is our theoretical yield now in mass units. 0.26 millimoles is equivalent to 142 milligrams. 0.26 millimoles of cholesterol dibromide is equal to 142 milligrams of cholesterol dibromide. Okay, so now we just determined that we made 88 milligrams of cholesterol dibromide, and so to calculate the percent yield now, you take the actual amount of product isolated, you divide by the theoretical amount of product that you could possibly make, and then you multiply by 100. So we are going to take 88 milligrams, which is how much we actually isolated, and divide it by 142 milligrams, which is the maximum amount you could actually synthesize. And so 88 over 142 times 100 is 62% yield. So that's a moderate yield for an organic reaction. And so that pretty much sums it up. And so be sure that you're able to do these types of calculations for the lab quizzes, worksheets, and also video journals.